You know, C has this legendary reputation. It gives you this incredible raw power. You're working right next to the metal. But that exact same freedom makes it ridiculously easy to shoot yourself in the foot, creating these subtle bugs and huge security vulnerabilities that can be a total nightmare to track down.
So that really brings us to the core question, right? Is C a tool of ultimate power or ultimate danger? Well, the thing is, the answer isn't to run away from the language. It's to embrace it, but with a really specific, disciplined mindset. It's all about building a framework of rules that lets you wield C's power safely and, most importantly, with confidence.
Okay, so let's dive into this. We're going to start with a fundamental design choice about something called encapsulation. Then, we'll tackle the single most important topic in C, memory ownership. After that, we'll build up a toolkit for writing clear and safe code, and finally, we'll zoom out to the professional mindset that ties this whole thing together. So our journey really begins with encapsulation. You can think of this concept as your first line of defense, the thing that helps you write C code that is safe, stable, and isn't going to completely fall apart when you have to update it 6 months down the line. So what is pure encapsulation? Well, it just means you hide the guts of your data structures. Anyone using your code can't just reach in and start messing with values directly. No, they have to use the functions that you provide. This gives you total control, it ensures your data stays consistent, and it makes your library way easier to evolve over time. Now, what's really fascinating here is the trade-off. Pure encapsulation gives you that rock-solid safety and control. But on the other hand, exposing a struct's members, what we're calling the performance approach, can sometimes let the compiler make better optimizations. It also means you write less boilerplate code, all that repetitive stuff for simple getter and setter functions. It really is a fundamental choice. Are you aiming for maximum safety or potential maximum performance? Now, that idea of control leads us straight into the most critical discipline in all of C programming, managing memory. Seriously, get this wrong and nothing else you do matters. But get this right, and you've already conquered half the battle. Take a look at this classic example. We've got a function here that uses malloc to ask the system for a new chunk of memory, and then it returns a pointer to it. But here's the problem, the real kicker. How does the person calling this function know that they're now responsible for giving that memory back by calling free? Just by looking at the function signature, there's no way to know. And this ambiguity, this is the root cause of countless memory leaks.
So it all comes down to this one simple rule. If you can burn this into your brain, an entire category of bugs just vanishes. If your function declares some memory, your function is responsible for freeing it. If the caller is the one who declares it, then the caller is responsible. Simple as that.
And check this out. This is the solution, and it's actually pretty brilliant. In this corrected version, the caller declares the pointer CPY themselves. Then they pass its address into the function. Now it's perfectly crystal clear. They created the pointer, so they know they have to be the one to free it. Ownership is no longer a mystery. Problem solved. All right, so with that huge question of memory ownership solved, we can start building a toolkit of practical habits. These are really simple rules that dramatically improve the clarity of your code and help you avoid some of the most common and, let's be honest, frustrating bugs out there. Each one of these is a small change, but they have a huge impact. First up, avoid generic void pointers. Using them is like putting a blindfold on your compiler. It has no idea what type of data you're working with, so it can't help you find errors. Sticking to specific types lets the compiler be your safety net. Next, be really clear about your data. Use uint8t quote pointer for raw bytes or memory buffers, and use char quote pointer only for actual null terminated strings. This just makes your intentions obvious. And please, always use the standards, like stdbool.h for true and false. It's portable, it's unambiguous. Now, this next one is crucial. Avoid static or global variables. Why? Well, in modern apps, you have multiple threads running at once, and if they all try to access that same variable, you get chaos, a classic race condition. It's a recipe for nasty, unpredictable bugs. And finally, prefer inline functions over those old-school macros. You get the speed of a macro, but you don't sacrifice type safety. All these little habits make your code more modern, more robust, and just plain easier to think about. Okay, here's a subtle but really dangerous trap. In this struct, we've got a 1-byte bool followed by a 4-byte int. Now, to align that integer correctly in memory, a lot of compilers will secretly insert 3 bytes of padding, just empty space, right after the boolean. This wastes memory, and on some systems like ARM, can actually cause your program to crash. And the fix? Oh, it's so simple.
Always order the members of your structs from the largest to the smallest. Here, the 4-byte int comes first, then the 1-byte bool. Bam! Everything aligns perfectly, no padding is needed, and your code is instantly smaller and more portable.
So we've been deep in the weeds with specific techniques. Now, for this last part, let's pull back and look at the big picture. Let's talk about the high-level philosophies that really separate someone who just writes code from a professional software engineer who builds reliable, maintainable systems.
You gotta embrace the Unix philosophy. Don't try to build these massive, complex, monolithic systems. Instead, build small, sharp tools. Write functions that do one thing and do it absolutely perfectly. Then, just like Lego bricks, you can combine these simple, testable, reusable pieces to build incredibly complex and powerful things.
All right, this next one is maybe the most powerful habit you can build. It's non-negotiable. Turn on all the possible compiler warnings you can. And then, this is the critical part, you configure your compiler to treat every single one of those warnings as a build-breaking error. A warning is your compiler tapping you on the shoulder and saying, hey, I think you've made a mistake here. You should always, always listen. You know, these are the little things that really separate the pros from the amateurs. Use standard types so your code works everywhere, not just on your machine. Always initialize your memory to 0 to prevent those awful bugs that come from uninitialized data, and test everything. C's simplicity makes it wonderfully testable. Don't compromise on quality.
So what's the big takeaway from all this? These rules, they aren't about limiting you or holding you back. They're about creating a structure, a discipline that lets you manage complexity. And it's that discipline that transforms C from a dangerous tool into an incredibly powerful one, giving you the confidence to build truly robust and efficient systems.
And that kind of leaves us with one last big question to chew on. We've talked a lot about C today, for sure. But think about these ideas: clear ownership, encapsulation, simplicity, treating warnings as errors. Aren't these the principles that define good software engineering no matter what language you're using? What we've really been exploring is a blueprint for discipline, and that's a tool you can take with you anywhere.